So in the last class we were discussing this the SU implant, right, and also the surface. So the ions have energy and they lose the energy, yeah, in position with the host material, meaning atoms in the host material, right? And we have also seen that when you do the installation, many times you use the mask, right? So the mask, you would like to. So the mask will also get the implant, and then the energy that is actually transferred to the host material and mask can result in temperature increase, and that could also lead to physical and chemical transformations in the host material. But since the temperature that you're talking about is not very high, you may have it confined mostly to the photoresist, okay, in silicon technology. But you should keep this in mind that when you're doing implantation, the implantation is not just used for this purpose, it is used for many other applications as well. So if the material that you're dealing with are sensitive to low temperature, they are not like silicon, meaning silicon also gets damaged, right, during the implantation, but you can recover, yeah. In this soft material, the recovery may not be possible. Or you may actually end up with some difficulties. For example, once the job of the mask is done, you have to remove it. So if that material has gone through some physical and chemical transformations, it may be more difficult to actually remove this things. So you have to use some special chemistry. Now, once you do the implantation, one of the important facts is that the implant will create damage, right, in the host crystal, and you may also want to. So you introduce the dopants, but then you may want to diffuse them further. Yeah? So you got a profile from the implantation, but you may want to diffuse it further. So this is a case where you have an implantation, and this is the implanted profile, okay, and we are talking about a Gaussian profile, okay, and then if you take a diffusion, so this is kind of you can think of this dose of the things that are already implanted. Now you're trying to diffuse it, okay. So if you look at this equation for implantation, right? So this is your concentration as a function of depth, and this is the total dose. Okay, this is the projected range, and the RP delta RP is the driver. Okay. So this is the Gaussian distribution. But on the other hand, if I take a diffusion profile, right, that also has a similar form. Okay. So this is from a fixed dose you are trying to diffuse, right? And in that case, you have concentration given by the equation for diffusion. Okay. So you have this is the total dose that is available for diffusion, and then this is the diffusion coefficient. This is the time of diffusion. Yeah. So you can see that these equations are similar in form. Okay. And if you look at this, right, you can see that 2 delta RC square, okay, and here 2 times dt. Okay, so you can say that delta RC square is equal to 2 times dt. Yeah. So there is an equivalence that you can find, and we had discussed when we are talking about the diffusion, and you have some diffuse profile, and then you are subjecting the wafer to some high temperature process, right? And during that, the profile would further diffuse, right? But it would preserve the Gaussian shape, okay? And then we had seen how to actually find out the meaning the new profile by actually taking the original profile and then you're fiddling with this number. Right? So you can say, okay, I implant this stuff and this is my profile, and I then further do a diffusion. Okay, so I would have to just modify this terms, right? And then I can get the new resultant profile. So this is rather simple. So you have this profile. So essentially you are modifying this, right, equation. Yeah. This has been modified, and so we said that delta P is equal to 2 times dt. So I take the equivalence of the equation. So you are just adding the thermal budget, so to say, to this equation. Okay. Yes. No, this position will remain the same. This is a peak position. Okay. So when x equal to Rp, what would happen? This becomes 0 and this is 1. Yeah. So the peak position will remain the same. That's what it says. Okay. So you have a Gaussian profile. The peak position will remain the same. It just comes down and then diffuses, right? And as you actually increase the diffusion time, it will go like this, right? And so on. Okay. But the peak position will remain. That's what this says. The peak value would actually increase with time. Okay. So if I substitute x equal to Rp, right? That position, this becomes 0. So, but as you increase the time of diffusion, this Cp, meaning the peak contribution is going to decrease. Okay, now if I look at the implantation profile, so this is something essentially what you're doing is so you have different dopants, for example, antimony, arsenic, phosphorus, and boron. The energy is identical. Okay, and the dose is also kept almost the same. So you can see what is happening here is that lighter the element, it goes deeper. Okay, so this is a very important observation, right? And obviously these profiles are not Gaussian, none of them. Okay, so this is not Gaussian, right? Okay, it's not symmetric about this one, so that you can see immediately. Right? So it actually spreads more into the surface. On the other hand, if I take arsenic, for example, and if I draw a line here, it's again asymmetric, but there is a long tail towards the depth of the surface, meaning of the substrate. Okay? So this is important, and you can see the antimony is coming here, right? This is the peak, and again this part is broader than the center. But for boron, it's actually different. So this part is broader than the. Okay. So lighter elements, you have towards the surface it actually spreads more, but in the case of heavier elements, it actually spreads more towards the depth of the beyond the peak. Huh? No, this is just implant. We'll discuss it in a moment. Why do you think this is the case? Heavier, yes, yeah.
So boron has a heavier energy, and it will go deeper into the substrate.
Okay, yeah, that is fine. So that explains why the Rp is higher for the same energy. Okay, but why this part is broader for boron. On the other hand, for antimony and arsenic, it's actually going in the opposite direction. Any guess? So this is basically, you can see segregation is when you have some reaction, right? And then a material interface is produced. So there is an interface, and which side do things prefer? That is segregation. Okay, but here it's not really two materials. We can see that the P concentration is about 10 raised to 2 into 10 raised to 20. So there's still how many atoms per, so 1 out of how many silicon atoms? Maybe like 1 out of 100, right? 5 into 10 raised to 22 is the density of silicon, right? If you're talking about 1 out of 200 atoms, so it's actually less than a percentage, half a percentage, even in this case. So it's not, you can't say that this is a different material. No, channeling we'll discuss shortly. So the thing is that here you have the light elements can be bounced back. Okay, so they're coming with heavy energy, but if really a big element comes, okay, it actually tends to go further. Okay? It is very difficult to stop. Like, imagine trying to stop an elephant, right? Okay? And it does not bounce. Okay? So it has larger moment. So this can go deep. So the boron can recoil back to the surface. So this is again boron. You can see the higher the energy. Okay, because it goes deeper. Yeah. So this is for 10 kV, acceleration 20 and 50. Okay. And you see this profiles. So these are auditorium simulations, and it's all scaled to a total dose of 10 to 13 centimeters. Okay. So again, you can see that if I am using small energy, then it is possible for me to approximate the implanted profile using a Gaussian. Okay. But as the energy increases, I can't actually approximate it with the Gaussian. So now, how do I model this? If I want to simulate this, yeah, I want to simulate a MOSFET, okay, and where I really would like to get realistic doping profiles, because doping profiles can influence the device characteristics. Okay, so if I want to do the simulation, I would really like to get the exact doping profiles in my simulation structure as what is there in my device. Yes. So what you usually do is to do what is called process simulation, right? Okay, so you should be able to reproduce an experiment in a simulation. So if I am doing an implantation and I would like to then simulate the resultant device, I would really like to get the same profile as in my experiment when I do the simulation. So there are many ways to do this. Okay, so for example, if I want to simulate a PN junction, so if I take a PN junction, right? So this is P inside silicon, okay, and if I do an ion implantation and diffusion, I get a profile like this. Yeah, this is the profile of, let's say, so this phosphorus, okay, phosphorus constellation, constant depth, okay, and I had this is my boron profile. Okay, so I have the junction here, okay, and I would really like to get this exact profile. So one of the ways to really measure the doping concentration, right? And I have many methods like secondary ion mass spectroscopy, SIMS, okay, or I can do what is called electrochemical capacitance voltage measurements and find out the doping profile. And then I use these doping profiles in my actual simulation. Okay, so that is one possibility. But then in MOSFET, advanced MOSFET, you actually do multiple implantations. Okay, and then you are also concerned about if I have a mask, for example, right? So this is my polysilicon. Okay, and I have a mask. This is my polysilicon mask. This is my silicon. And I am doing an implantation. And it's very difficult for me to use any of these techniques to find out what is going on around this. Okay, so that is why we would really like to get a good simulation model for the vertical and then apply that here to find out what would be the profile also laterally. And then also for the junction, meaning so this is let's say an N-channel MOSFET, right? And this region you create by multiple implants, 2-3 implants. Yeah, so it becomes quite tedious to do the actual network. So you would need a model, and one of the obvious thing then would be to actually use shrimp kind of simulations, right? You are doing statistical simulations. Okay, you are simulating some 10,000 ions that are implanted, okay, and then you build a statistics, a distribution based on the result of the thing. But then it is going to take a lot of time, and it's not very efficient in the sense that you don't have. It may be accurate, but it may take a lot of time and also computational resources. Okay. So you can easily realize that if you do a shrimp simulation, you can download this program and run it on your computer, and then if you actually simulate it for let's say 100,000 ions and see how long it takes. Okay, just one. Okay, but in a MOSFET you may have to do maybe 10 implants, so it's then going to take a lot of time. Okay. So this is something that we already discussed. If I look at it, so this is contrast between boron and antimony, and the energies have been chosen so that you have exactly same projected range. Okay, but then you see the asymmetry in the profile. Okay, so antimony goes deeper. On the other hand, boron actually spreads more to the surface. And the reason is something that we've already discussed. So boron is lighter, so it can actually be bounced back towards the surface. Okay, so now how do I model the implant profile? So it's very clear that it is actually not a Gaussian, right? And in Gaussian profiles, you have what they call as two moments in the distribution. So one is the projected range. Okay, so there is a mean of the distribution, and the other is standard deviation. Yeah, but that would actually not describe your implant profiles except for low energy. Okay, so that we have seen. So what is usually being done, instead of using a Monte Carlo based simulation, which can take a lot of time, you fit the actual implants right? So you have actual implanted profiles, and then you do SIMS measurements, okay, a lot of SIMS measurements to find out what is the real implanted profile. Okay. So I think I mentioned what SIMS is previously, right? You are actually bombarding the surface of the silicon using gallium ions typically, okay, or cesium or gold, for example. These are other things that have been used, but they are more expensive, so people tend to use gallium, and then you basically sputter, yeah, atoms from the surface. Essentially, they will be ionized. So this is called the secondary ion, right? Primary ion is actually what we use for gallium. And then you analyze. So you use a mass spectrometer, and this is nothing but a magnetic sector, for example, right? So that is one way to do this. So you have seen this. If I have a curved path, okay, so I have a magnetic field, okay, and I can steer the ions through this, okay. So depending on the mass and the charge, so if you fix the charge to unity, and then this path, so and a particular ion would take this path if I apply a certain magnetic, yeah, the field on, meaning the force on the ion would be Q times V cross D. Okay, so I isolate the ion and then I steer it along this path using the magnetic field. So if I know the V and the B, then it is possible for me to find out what is the mass of it. Okay, so I can then find out which element it is. I can even actually distinguish between isotopes. Yeah, that is possible. So that is one. So you do this secondary ion mass spectroscopy, or you can actually, there is another technique called time of flight. So you get these ions out, and then you have a collector for these ions, right? Detector. How long it takes the ions to travel through it. Okay. So that would actually depend on the velocity of the ions. Yeah. So I can. So they actually are ejected with a certain kinetic energy, and then you apply fields to distinguish these ions based on the time they take. Okay, so this is so you basically do a lot of experiments, find out the profiles using SIMS, and then you develop a library of implant profiles. Okay, so instead of now I can create huge databases of implant profiles, right? And then I can look up, yeah. But then it is going to be quite costly in terms of storing this information. So one of the easier things would be to fit some kind of distribution. Okay, so they use what is called a 4-moment distribution. So in addition to the range and the triangle, you add 2 more components. The skew. So, for example, in the profile here, the skew would actually indicate which way it is deviating. So this is my Gaussian, so this would be the skew. Okay? Meaning, this part can be taken care of by defining a software. It is skewed in a certain way. Okay? And another parameter is what is called the kurtosis. And these are defined. So we will not go into details here. So usually what they use is 4-moment Pearson distribution. Okay. So this is much more computationally efficient than doing Monte Carlo solutions. Mm-hmm. Yeah, so I should admit I don't know about this, so I can look up and tell you. But this is the skew is says in which way it is actually tilting, right? Towards the inner side, or so it's actually talking about some asymmetry in the profile. Process, I don't exactly. This would be the symmetry part because it's actually an even power. So I don't actually. Let's for example, I would imagine that there is an asymmetry in the case, but not so much. But you see that tail that goes in here, like maybe this is what. Okay. So a tail that is actually, in this case, you can see it goes down, straight down, right? But here you have something that is. This may be, but I'll check. So now the other problem in implantation is channeling. So shrimp, by the way, shrimp would actually do the simulation of implantation to amorphous material. Okay, not to crystalline materials. Now in crystalline materials, there are certain other aspects. So, for example, channeling. So you can see this is something we have seen in our module on the crystal growth, right? This is the silicon crystal and projection of the crystal on 100, and you are actually looking at the 100 direction. Okay. So you see this nice thing, but if you go back to the previous, the one of the, I think, second module or so, you will find projection of the crystal on different planes, looking at from different angles. Okay, so you can see the open spaces, right? Yeah. So if I shoot, let's say, small ions like boron, they could go deeper. Okay. So this is, for example, something you are looking at from this side, right? And you see a channel. Okay. So if I now shoot ions straight in, they may go deeper. The ions that hit the channel may go deeper. Okay. So that is the idea of channeling. So they may actually get deflected, low angle deflections, and then go much deeper than an ion that would actually make a head-on collision with the atoms. So this is, but then the channeling requires, so when you do the implantation, channeling will happen if the material is crystalline. Okay? Very important. So this is a comparison of two implants. Okay? One is done at 2 × 10⁻13 dose. Yeah? And this is 2 × 10⁻15 dose. Okay? So obviously you have, the higher the dose, yeah, you got this going deeper. But then you look at the shape of things. Okay? And so this one is more flat, right? And if I just scale this to the same dose, okay, meaning I take this profile, but the integral is made to same as this. Okay, so it might go higher, right? Meaning it is just scaled up, okay, multiplied by some factor, okay, and it shows that if I were to scale it to the same number, but preserving the profile, okay, so this one would actually look deeper. That's what it says. So you can see in this, where as you increase the dose, more and more ions actually end up in this part of the profile. Okay, and here you cannot say that because it's actually looking fairly flat. But in this case, it's peaking somewhere here, and then there is a substantial reduction. Now this can be explained by channeling, because as you increase the dose, you're creating damage in the crystal. As you are increasing the dose, right, more and more ions are coming and hitting the silicon, so you are creating more damage. So now the crystalline structure is destroyed, and as a consequence you can't have channeling. So this part of the distribution is more for low dose implants. It looks more flat because of channeling. Okay, heavier the dose, but then after certain implant dose, the surface part is actually severely damaged. So you would have most of the ions ending up in that region. Okay. Now, how do I model this? Because this actually, I may be able to deconvolute this into two types of profiles, right? If I take this, okay. So then, so if I want to use the Pearson model, 4-moment distribution would not be sufficient. So what is being done is a dual Pearson. So essentially, two distributions, right, are used. Okay. So each one would have 4 moments. So this would actually have 8 moments distribution. Dual Pearson model is used in simulations. Now another thing is shadowing effect. So the ions are actually approaching this substrate by with certain direction, right? Because you're accelerating the ions. Okay. So you can create shadows. So for example, if I take a wafer, now why do I want to tilt it? Okay, so first of all, why do I want to tilt the implantation? So you don't actually have the channeling power. Okay. So if you go back to the previous slide, right? So what you're saying is that instead of implanting it like this, okay, you implant it with a tilt. Yeah. So so you tilt the beam, or typically you tilt the wafer. Okay. So if I start to now tilt it, the tilt angle is defined with reference to the vertical to the substrate and this angle. Okay, this is a tilt angle. Okay. So now I make, you have a gate here, so it actually would have a shadow. This gate would actually create a shadow. Okay. So any topography can create a shadow in the implantation. Now if I make this MOSFET, let's say this is my source, this is the drain. Okay. Would this device work? This is source and this is drain. So I can think of two scenarios, right? This is my gate. Okay, this is one scenario, right? This is source, and there is nothing holy about this definition of source and drain. So I actually take this. Yeah, okay, this is correct. Okay, so which transistor would work? Which will not work? None of them will work. Everybody agrees? Or anybody disagrees with this? No opinion? You are not planning to go to Australia. This may work. What about this? We say that first one will work. Yeah, just try it out. No? Which one will work? So usually, what do you do when you have a source drain? Meaning, let's take this is an N channel MOSFET. N channel MOSFET. So you just draw the MOSFET and apply the what kind of voltage you apply? Source to drain voltage, right? The source will be grounded and the drain will be positive. Okay. So now you tell me what would happen. So you can also draw this as N plus source and drain are N, and the channel, this region is P. Okay. So I say one of them will work under what condition? Also, you tell me. What is drain bias? Drain bias is provided. So she is saying that first one will work. So this is 1. Yeah. 2. So she is saying that first one will work. Do you agree? You don't agree? Why don't you convince? Which one will work? So you were saying something, right? Hey, forget about short term effect. Life is simple. No, you see, saturation, I always say this is something that we define, right? Yeah, but what happens? You tell me, so when I am using a transistor, right, a MOSFET, what am I trying to control? From the gate, the channel, okay, and then, before the channel is formed, what am I trying to control? So, if MOSFET has two parts of the characteristics, right, what is it? So, you are doing your device course, okay, VGS ID, okay, and I plot the law of ID. Okay. Log of ID. On the other hand, if I plot this ID linear scale, go like this, right? Yeah. So this is an exponential increase. Okay. So when you look at the textbook model, right? Textbook model of MOSFET, who tell you what is going on here? Yeah. Till this point, the current is 0 in the textbook model. Okay. But this is exponential. So here you can say, okay, I am just controlling the channel, I get it, right? I increase the current when I have more electrons in the channel. What about this part? So this part you are trying to say, okay, I am controlling the channel. But here, what is happening? So this is an exponential curve. So let us see this. An exponential, right? So you have actually on a log scale, you plotted this. You can identify this thing as, okay, something is happening here, and what is happening here is not the same. So usually we say that, if I plot a log plot, and you have two slopes. Okay, so this region is something happening, and here there is something else. Otherwise, this would have continued. Okay, so we have seen this model, right? Reaction model and so on. So if nothing was limiting the current, okay, it would have just increased the current. Okay. Otherwise, this would have gone like this, right? So the current is limited by some process here and some other process. Okay. So what is this? Yes. So diffusion means what? Yeah, but why the diffusion is important? You can see that you are actually see this part. You may want to go back and check this. This part is essentially the characteristics of the PN junction diameter here. Okay. This is reverse bias, right? And so there is no way I can get this voltage here unless short channel. But you forget it. So I am actually controlling this PN junction by applying a gate bias. You get the point? Right? So that is why this is actually PN junction characteristic. This part. Okay. Source to channel junction. So I need this. I want to, so basically electrons are here and you are lowering the barrier for electrons to flow into the other region. Okay. This is like you are forward biasing the PN junction, essentially. Okay. So, but this in this case you are actually doing it by coupling the voltage to the PN junction through a capacitor. That is a gate capacitor. Right? So this is what you are doing. Right? And when you do this process, so you want, in this case, I have no control on this junction. I would lower the potential here, but not at the junction. Okay. So this device will not work. But here I can control the PN junction. I get the channel, and this is reverse bias. So if the reverse bias junction depletion region can go under the gate, I can get electrons. You can see that the PN junction, right? The moment you get carriers into the depletion region, very high field, there will be substituting. Okay? So a reverse bias PN junction does not conduct because there are not enough minority carriers on the two sides, right? But you have this situation is changed, so you have they can be swept to this side, no problem, right? So this would work, and this may not work. Actually, this will not work. Okay, but of course, this case is not very good. Meaning, you have a transistor that has this kind of structure. You may end up with higher series resistance on the drain side. Okay, it would still work. So there actually some people have used this. For example, one of the dual degree student, Hemant Deshpande, actually we were, attending courses. I was doing MTech here and we were doing dual degree. So we used to attend lectures together and so on. So this guy designed for his PhD, developed an asymmetric transistor. Okay, this is an asymmetric device. Right? The junctions are not identical, so this can be used for certain applications. So he actually developed this for some analog mixed signal applications, which was later on actually implemented by Intel in some of their devices, products. Okay. Now the shadowing effects can be much more tricky in 3D structures. So we are talking about a thin FET, for example, right? So this is my fin, okay, and this is the wafer for the direction. And then if you look at this image, this cartoon, so what is being drawn here is actually a section along this, right? Yeah, the vertical section along this. and you are looking at it. So this is my tilt. Okay. But then when I do the implantation, and if I just tilt it with reference to the plane, meaning a line perpendicular to this, right? I still have a problem, because how do I implant? So this is, the gate will be on top like this, and this would be my source. This would be the drain. Okay. So I should, what about the sides? Yeah? Because this is my source, and I implant it only from the top. Okay. I need to get the dopants deep down till this point, right? So I may not actually, then I need to use a very high energy. Yeah? But still I will not get a uniform profile. Okay. So what is then being done is to do what is called a twist. Okay. So you take this wafer and you have tilted the beam, okay, this way, but you are also twisting. So this is my fin looking from the top. Okay. So this is the fin, and I also apply a twist to this. Okay. So then I need to define this. So I have a twist like this. So this part of the fin would get implanted. Yeah. What about this part? This side. Okay. I am implanted from this side. What about this side? Okay. So then I need to rotate this wafer and implant it from this side. Okay. So the moment you define a twist, okay, and in fact I can also define. So if I go back to the previous one, okay. So how do I actually then avoid the shadowing effects in the previous case? How do I avoid the shadowing effect in this case? Yeah, so you rotate the wafer. Okay. So you can continuously rotate, or you say, okay, I would implant it like this one, right? And I implant, half the rows will be this way, half the rows will be this way. Okay. So that is called two-quadrant implants. And in this case, you are going to implant to avoid the problems, because tilt I need to implant this way and this way. But to avoid the shadowing effect because of 3D, I need to implant it from all four quadrants. Okay. So now, how do I specify the implantation process? So I can look, say, okay, which species I want, right? And then energy. So this will decide the range, struggle, skew, and kurtosis of the implantation. Dose will decide the total reconciliation, right? And the P-concentration and so on. And tilting is done, tilt is specified to get rid of channeling. Twist, tilt and twist is again to avoid shadowing effects. And you also need to specify, or you can specify the number of quadrants. Yeah. So if you don't specify, or you can actually say one quadrant, then you get this asymmetric devices. This is also possible, right? So this is one example. So you actually say, okay, I want to implant arsenic. This is the energy, dose, total dose, tilt, zero twist, 4 quadrants. Okay, so now before we proceed, if we talked about channeling, so what would be an obvious way to avoid channeling? Tilt is one option. What is the other option? What could be the other option? So you create an amorphize the silicon. How do I do that? Okay, I want to implant boron. Yeah. So what is saying is that amorphize. So even yes.
By taking some another material and implanting it at a higher energy.
So what is saying is that implant some other stuff, not boron, but many times the other stuff can be silicon itself. Yeah. So the objective there is to just implant and create damage. Okay, amorphize the initial couple of tens of nanometers. Another popular ion is actually species is germanium because they are heavier. Okay, so that is called, then if I do that, it's called a pre-amorphization implantation. Pre-amorphization implantation. Okay, before I shoot the actual dopant ions, I amorphize this by using silicon or germanium. Okay, ion stopping process is something that we have already briefly discussed. So you have the nuclear stopping, okay, so where the incident ions interact with the nuclei of the, the nucleus of this interact with the nucleus of the host atoms, and they would actually, the incident ion may get scattered and the target can get displaced and so on. And then you have electronic stopping, two kinds. One is called a non-local electronic stopping. So what happens is that this is your ion, right? And as it enters, electrons gather around it, right? And electrons then tend to pull it back. Okay? Because this electrons are bound to atoms, right? So that is one process. The other is that you actually have this ion that is coming in, and this is a transit atom, and the electrons in the outer shells actually interact. That will lead to some scattering. Okay? So this is the other. So these are what are being actually simulated in shrimp, for example. Okay? Now, the damage due to ion implantation. So this is an interesting thing, because I mentioned that if I, to create interstitial vacancy pair by dislodging a silicon atom from its lattice site, you need about 15 electron volts of energy. Okay. So if I implant ions with an energy of 15 kilo electron volts, let's say. So in principle, they can create 1,000. Each of these ions can create 1,000 displacements. Okay, but you have just implanted one ion. Yeah, you get the point. So if I count all the displacements, for example, this is an example of a shrimp simulation at 100 keV and a phosphorus. With a dose of 10^15, and you get the implanted profile like this. Okay, but you see the displaced silicon atom. Yeah. Is there anything interesting about this? So of course, the displacement is, if I take 10^20, 10^23, so almost 1,000 times. Yeah. So each of these ions cause multiple displacements. That's what it is, right? Anything else? Okay, so you can see here the displaced silicon is actually more than the concentration of silicon. Right? Essentially, it means that you have displaced, hit and moved a silicon atom multiple times. The same atom has been displaced. So it can also happen that you actually dislodge an atom from its crystal lattice side, lattice position, and then another ion came and hit it, and then it put this silicon back into crystal side. Okay, so this is possible. So it's actually you create damage, but also some of the damage can get annealed during the implantation process. So this is, for example, you can see the cross-section TVM images of silicon implanted with something. So this part has actually become amorphous. Okay. So this is how crystalline silicon would actually look, right? So before implantation, the whole thing is like only this, right? the whole region would be only crystalline silicon, but after implantation you can see the amorphous silicon. And also further into silicon, if you look very carefully, there are actually local damages that have been created in the silicon. So we'll discuss that and I'll show you some more images. So this is something that we had seen previously. I'll stop with this slide. So you have a silicon in substitutional site. You are actually dislodging it from the substitutional site, right? This is actually crystal location, right? A lattice site. So if you dislodge it, you get an interstitial and a vacancy. Okay. But you dislodge the silicon by implanting a dopant atom. So, and this is the ion direct sound, which causes the displacement. So, and then you do the annealing, for example, yeah. So you can have interstitial vacancy recombination. This leads to a silicon, the silicon getting back to the substitutional site. But what about the implanted ion? Because you created an interstitial and a vacancy, and then you have a dopant. Now you annealed it. The silicon went back to its position. Okay, what about the dopant? It's not active because it is not in a substitution, right? So the other possibility is that the dopant reacted or actually combined with a vacancy, so it actually occupied a substitutional site. So it is active. But what about the silicon atom that it has dislodged? Okay. In both these processes, you will create defects. Yeah. So this is when you do the annealing, both this will create one defect. Okay. This can be a silicon interstitial or a dopant, which is at the interstitial side. Okay. So this would create, by the definition, a defect. Now we have seen discussed this previously that a lot of processes, for example, oxidation, okay, diffusion, all these things are actually controlled or influenced by presence of defects in the silicon. Okay. So when you do the ion implantation and you try to anneal the damage, you will always create defects. Okay. So anything that you do after this would be, then you have to take this into account. Okay. Very important. Okay. So we will have a lecture tomorrow. Yeah.